Hi, so this new topic, organic chemistry. Before I get into it, I want you to understand that this topic, organic chemistry, is about carbon and carbon compounds. And the size of it is that the topic is bigger, this organic chemistry, is bigger than the whole of the rest of chemistry put together. This is the chemistry of living things, and consequently plants, animals and the chemicals that make them up, etc. are all organic. 95% of all chemistry is this kind of chemistry, organic chemistry. Most people who are chemistry experts are working on problems within organic chemistry, making drugs, understanding how plants and animals work, etc. It's all organic chemistry. So topic is really important, and it's huge. Now within GCSE it's just one topic. Within A-level it's a third-ish, and at university it's just under a third if you bring theoretical chemistry into it. But what I'm trying to say to you is it's just one topic within GCSE does not give it enough justice. And I want you to pay particular attention to this topic, because the chances are you're going to carry on at A-level and you're going to be involved in chemistry and you're going to be involved in organic chemistry. Let's get into it though. So where does the story start with organic chemistry? It starts with crude oil. Now crude oil is found in the ground, and we often drill through our ground, through the Earth's crust to get to it, either on land or we drill on oil rigs in the sea, but we get through the sea onto the Earth's crust and we drill through that to get the oil reserves that are on our Earth. But what are those oil reserves? How do they come about? And what chemicals are within them? Let's get into that then. So, the story of oil starts millions of years ago. Now, another word for oil is petroleum. You may have heard of the phrase petroleum industry, or the oil industry. And that's in reference to all of this. And plants and animals from millions and millions of years ago died. And when they died, they fell onto our Earth. They fell onto the crust of our Earth. And then, as they start to decompose and break down the remains of plants and animals over millions of years, then rocks, new rocks, tend to form on top. The idea here is that nearly everything gets washed into the sea. So the plants and animals from millions of years ago that died would have been slowly washed into the sea, and then new sediment on top makes sedimentary rock on top of those remains of plants and animals, and the new rock presses down. The new rock pressurizes the remains, the plants and animals from millions of years ago, and as they get pushed further down the Earth's crust, they get closer to the mantle of the Earth, which is hot. And the hot heat from the Earth's mantle warms up these remains. And the warmth of the Earth speeds up this decomposition. The pressure of the rocks on top speeds up the decomposition. The time, the big time lag, the geological time scale, being lots and lots of time between then and now for all this decomposition to occur. And now we're at a point where what we've got are the remains of plants and animals. And those remains we call fossil fuels. So the remains of plants and animals, the remains are known as fossil fuels. There are three fossil fuels: coal, oil and gas. So the solid remains are the coal, the liquid remains are the oil, and the gaseous remains are what we call the gas. And typically we find gas above oil and where the oil and the gas have escaped, then we just find coal. So crude oil is one of these non-renewable resources. You get questions at GCSE asking you about what kind of resource it is. Wind power, wave power, solar energy are all renewable sources of energy. I don't want you thinking that you can remake more oil by letting plants and animals decompose, because the time is huge. Huge time spans stop you calling it a renewable resource. And certainly the rate at which we use up our fossil fuels, coal, oil and gas, is much faster than the rate at which, if you let the current plants and animals die, the rate at which the fossil fuels would be remade would be much smaller. So the making of these fossil fuels is slow, and it would not replace the fossil fuels at the rate that we're using them up. So never call it renewable. This is it's crude oil is a non-renewable resource. And the term crude oil is used to talk about the raw oil we dig out of the ground. So when we drill down into the ground, come to some oil deposits, and we suck up the oil deposits, they are called crude oil. Now, I've tried to search the internet for a diagram to give you the right idea in your head about how crude oil was formed. And I like this diagram because it seems to be rich in plants and foliage, and those plants and animals that are not there, but if you could imagine some animals in there as well, they dying first, as they decompose, they make something called peat, and then as the decomposition carries on over time, that peat is called lignite, and the lignite over more time, finally we're left with coal. And the liquid remains, as I said, will be oil, and the gaseous remains. When things break down, there's often gas coming off, and that gas is known as natural gas. So natural gas, crude oil and coal are the three fossil fuels of our world, and they're all formed like that. They're all formed from once living plants and animals from millions and millions of years ago. They've undergone decomposition over time, with pressure pushing them down, and with the heat of the earth warming up and speeding up that decomposition, which takes a long time anyway, but the warmth of the earth has managed to speed that up. So if we look, maybe this is some oil here, the oil is in black, then we normally find gas on top. And when you look at an oil rig, they're burning the excess gas for safety reasons above the oil rig. Well, that's the gas we're talking about. The gas that you have in your houses that is used for your gas boilers, and gas that you might use for cooking and roasting your chapatis that you eat on a daily basis, that gas is this gas here. It's called natural gas, and it's piped from oil reserve, above oil reserves. It's piped through big pipes to our homes, and we use it. Now, underneath the gas is the oil, and above the gas is caprock. Now, caprock is impermeable. Caprock stops the gas from escaping because it doesn't let anything escape, and it stops the oil from escaping. It's like a watertight, oil-tight, gas-tight barrier which prevents the escape of gas and oil and keeps it there. Now, often you get water as a product of decomposition of living things. So the water, the decomposed water, being more dense than oil, sinks and is found under the oil. So by drilling holes, drill holes here and here and here and here and here and here in 2 dimensions, drilling holes allows you to get an idea of how big that oil field is. And therefore you can guess, once you've got some holes drilled, whether it's worth trying to get that much oil out. Small amount of oil might not be worth setting up an oil rig. Huge amount of oil, then of course, set up an oil rig, get the oil out, pipe the gas to people's homes, and that is the industry that British Petroleum or Shell as a company are involved in, and they're called petroleum companies, and they make their money from selling the products of crude oil. But crude oil on its own like this is not so useful. Crude oil, when you dig it out of the ground, you can burn it, but there's very little else you can do with it. So apart from burning it, there's little else you can do, and therefore, in order to put it to good use, you've got to undergo some processing of it. So you've got to take it to an oil refinery, a processing plant that will separate crude oil into much, much more useful separate things, which we call fractions. Now, what chemicals are in crude oil? Well, crude oil is a mixture of thousands and thousands of different hydrocarbons. Now, these are hydrocarbons. I've just made a few models up. The black ball is carbon. The white balls are hydrogen. And carbon and hydrogen together make something called a hydrocarbon. Now, that's a hydrocarbon called methane. And I'll be coming back to that in the next video. But that's the main component of natural gas, what you're burning at home. But anything, so long as you've got carbons and hydrogens, that's ethene, that's butane. I'll come back to molecules on the next video, but all of these are hydrocarbons. Can you see? They're made of carbon and hydrogen atoms only. So the definition of a hydrocarbon are compounds that contain carbon and hydrogen only. You must put the word only in exams, otherwise you're going to lose a mark. So crude oil, big, complex, lots, thousands of hydrocarbons, all different types. And this topic, we will get into the different types of hydrocarbons that we find within crude oil later. Not this video, but some other video. What's useful then is to take this crude oil and separate it. And if you remember, crude oil is a mixture of different liquids, and we need to separate them. Then if you go back to work we've done this year, one sensible way of separating liquids is fractional distillation. So you have to do fractional distillation. And fractional distillation will separate crude oil into much more useful, much more valuable things that we're going to call fractions. But let's go back to what was fractional distillation when we talked about it earlier. What was it? Well, let me show you this diagram. That was simple distillation, if you remember. And this was fractional distillation. Fractional distillation had this extra fractionating column within it. And that extra fractionating column gives you good separation of liquids. Whereas simple distillation does not give you good separation of liquids. That's like more to separate if you've got a solution and you want the solvent. Well, then you use simple distillation. If you've got liquids, use fractional distillation. So, fractional distillation of crude oil. You need to know about this. Thousands of different hydrocarbon molecules are within crude oil. And they all of them have different boiling points. So if we put crude oil into a fractional distillation column, and then we can try and separate it based on their different boiling points. The thousands of crude oil chemicals that are within it are separated into things called each fractions. Now, each fraction is not pure. Each fraction is a mixture of chemicals. But within each fraction, the boiling points are similar. And this fractional distillation is done as follows. Now, you're going to have to learn the fractions. So let me explain how it works, and then I want you to learn the fractions. Crude oil. Crude oil is put into a big, tall fractionating column. That fractionating column is about 5 times the size of your house in height. And at the very bottom, you've got big heaters. So the column is hot at the bottom, and as you go further up, it gets cooler. And at the very, very top, it's pretty cool. It's like room temperature-ish, like 25 degrees, like a warm room at the very, very top. So there's a whole span of temperatures from warm at the top to incredibly, well, not incredibly, but 500 degrees-ish, 500 degrees at the bottom. Now, imagine your chemicals going into the bottom. It's very hot. So almost everything will turn into a vapour. Almost everything vaporizes or boils. And all the chemicals start rising up, and they go up. The ones that don't go up make a fraction called bitumen, which you guys may call tar. But tar is used to make roads, and tar is used to waterproof roofs. So roofs and road building depend upon this fraction. We call it bitumen, and there, roads and roofing. And that's one of our fractions that we get. And bitumen is not pure, it's not one chemical. It's a mixture of chemicals, but they all have very, very high boiling points because they are the things that don't boil. And they collected as bitumen, and that's what tar is. But imagine everything else that's boiling. The vapours will rise up this column. As they go up and up and up and up and up and up, the temperature goes down and down and down and down and down. So all the vapours, as they're going up, eventually hit their boiling temperature, their boiling point. If something boils at, say, 150 degrees, it'll go from here and it'll reach about here. And there, the temperature will be about 150 degrees. And when it hits 150 degrees, it'll turn back from being a gas into a liquid. That's a process called condensing. So as the vapours go up, they condense. And depending upon their boiling points, they will condense at different heights. The higher the boiling point, the lower down they will condense. So if the boiling point is like 300, then it will turn into a liquid round here. See, 270, 300. 300 degrees, it'll turn liquid about where my hand is. 200, it will turn liquid where my hand is now. 70 degrees, it'll turn liquid where my hand is now. So as the vapours go up and the temperature goes lower and lower, eventually every chemical that's got a boiling point above 450 degrees and below about 70 degrees will liquefy or condense. And that word condense, learn it. Get gases turning into liquids, condense. They condense, and when they condense, they come out of the closest exit to their height. So at the very, very top, this one is petrol. But what about things that haven't turned into liquid at all? Well, there may be some things that go all the way up and they haven't turned into gases. Sorry, they stay as gases. They haven't turned into liquids. Well, they're what we call the gases fraction. The gases fraction contains propane, which is a camping gas. It's found in red canisters. The blue canisters are butane. So these gases are the, if you're into camping and caravanning, those bottled gases are these things here, refinery gas. I once had a car that ran off LPG, liquid petroleum gas. What it is that fraction. If you press it, if you compress it, it turns to liquid. Stick that into a car, try and burn it. I mean, my car was not great. It had all kinds of problems because the technology didn't work on it as it was LPG, running on LPG, and I scrapped it in the end. But it was an interesting attempt by me to be more green in my motoring. We'll talk about that later sometime, but let's get back to this. Gases, one fraction. Fraction underneath, petrol. Now, largely petrol are chemicals that have turned back into liquid, condensed, around 70 degrees boiling point. So, pretty low boiling point. That's why petrol turns into a gas very easily. Petrol's volatile. We use the phrase volatile when things turn into a gas. Petrol. And then the next fraction, naphtha, 120 degrees. Now, naphtha is the chemicals from which the petrochemical industry, the pharmaceutical industry, they use naphtha as a starting material to make all the medications of our world. Really important fraction. After that, the next fraction, chemicals that boil around 170. Jet fuel called kerosene. Next fraction, chemical that boil around 270. Diesel. Diesel cars, diesel is used to power lorries and big HGV trucks, etc. That's what we're talking about, normal diesel. Lubricating oil is the oil you put not to power your car, but to help the metal rub against each other without generating too much energy and heat in your car engine, etc. Lubricating oil. And then fuel oil is the fuel we put into ships. So what I want you to learn is, I want you to learn gases, petrol, naphtha, kerosene, diesel, lubricating oil, fuel oil and bitumen. Now, find some memory aid to learn those in order. Every now and again you get GCSE questions that has a diagram with one name missing and they want you to fill in the name. So learn about it. And then there are lots of patterns that happen to the chemicals that are within. Now that's my next video. I'm going to deal with the chemicals that we find in each fraction and how they change, like how their boiling point changes, how their viscosity changes, how their volatility changes, etc. But that's for the next video. For this video, I want you to learn the names and I want you to learn some uses. So for each one, I would learn a use. The uses are there. Learn them with the names. And that is a really important slide. And you get questions on that so frequently. So learn it. Right, so fractions. What are they? Well, fractions are valuable. Define a fraction. A fraction is a collection of chemicals. A collection of chemicals. So it's not pure. It's a mixture. Fractions are mixtures collected by fractional distillation that have similar boiling points. Similar boiling points. That's what's crucial. And collected by fractional distillation. Fraction. So collected by fractional distillation, similar boiling point, chemicals, mixture. That's what a fraction is. So the lighter fractions are in greater demand. There's more demand for petrol and less demand for bitumen. Petrol at the top is in more demand, bitumen is in less demand. The lighter fractions are in greater demand. And they are collected at the top of the fractionating column. We sometimes use the phrase, they are the heavier fractions, as opposed to the lighter fractions that are in much more demand. Now let's look at these fractions. Now, the boiling points. As you go down the fractions, the boiling points increase. Viscosity is how thick and gooey something is. The viscosity increases. Flammability is how easy it is to burn, and they become more and more difficult to burn. So the flammability decreases. Chain length. Chain length is how many carbons. Like this molecule has got 4 carbons. How many carbons? Like petrol is made of molecules that are about 8 carbons long. So 8 carbons, and bitumen is like more than 50 carbons long. Carbon chain length. The chain length, that's the chain length, how many carbons per molecule gets longer and longer and longer as you go down the fractionating column. And then finally, I've added one there about colour. Sometimes they ask you about colour. The fractions tend to get darker and darker and darker as you go down. So petrol is almost colourless, but there's a tinge of yellow. Pale yellow mixture. Whereas bitumen is dark, very dark, black solid. So there is a trend. As with so many things, there is a trend, and you need to know the trends in terms of boiling points, viscosity, flammability, chain length and colour. So learn those trends. How about demand? Well, percentage number, sorry, no, this isn't about demand. This is about how many carbon atoms and boiling point. How many carbon atoms? You see, as the carbon atoms get longer and longer and longer and longer and longer molecules, then the boiling points get bigger and bigger and bigger and bigger and bigger. Bigger molecules, the boiling points get bigger and bigger. And if you look at percentages, now that will be one crude oil. They'll have 2% there, 34% there, 11%. Different crude oils from different places around the world have different breakdown of the various fractions that we're talking about. So that is just another diagram that gives you the same kind of things again, gives you uses here, but now we've got chain length. The molecules getting longer and longer and longer as we come down is extra in that column. Supply and demand. Say you've got a crude oil with these fractions, percentages. But what you actually want are these percentages in the real world. For example, you want more petrol and you get, by doing fractional distillation, you get less petrol. So it would be great if we could convert these larger fractions that are in oversupply. Look, you make 50% of a crude oil may be tar or bitumen, but you only need 38% of that. So not of that, you need 38% in total. So out of the 50%, you only need 38%. So you've got 12% extra that you don't need. So there's an oversupply. There's an oversupply. Look, I've written oversupply. There's an oversupply of the big fractions and an undersupply of the small fractions. It would be good if we could reconcile the supply with the demand, and we do so using a process that you need to know about, and that process is called cracking. So to satisfy world demand, you've got to take some of these bigger fractions and turn them into smaller fractions. Well, how do we do that? Well, we do it by just heating them. Heating it very high temperature, then the molecules will literally, if you've got molecules like this, if you heat them up, they move so much that they start breaking apart. The long molecules start fragmenting into smaller molecules. Let's have a look at that next. So the way that this diagram makes you think is, I want you to think these are carbon chains, long carbon chains. When you heat them up, they will break up into smaller carbon chains. That is cracking. That's the process of cracking. So catalytic cracking will turn large, long molecules into smaller molecules. And really, what I want to leave you with is this equation. Now, next lesson I'm going to explain to you what alkanes are and what alkenes are. But basically, I want you to learn that cracking will take the long molecules, larger alkanes we call them, take the large molecules. If you've got catalyst and high temperature, catalytic cracking, high temperature and catalyst, then you'll get smaller alkanes, which are smaller molecules, and you'll get something called alkenes, which are a new, breed of molecule, a new family of molecule that I'm going to talk about next lesson, next video. So I think I just want to leave you with that, because that equation in red, is where I'm going to pick up from next lesson. And I'm going to talk about molecules like these, because a lot of questions are more about the molecules rather than the processes of. What I hope I've done with you is how fossil fuels form, how crude oil, the petroleum industry, is important, the oil industry, how they do fractional distillation, and how we need to do cracking to satisfy the world demand for all those fractions that have such important uses. Learn your fractions, learn the uses, learn the trends, and I'll see you next video. Okay.